In this video, we are going to look at a few word problems. So let's start with 91, movement of a minute hand. The minute hand of a clock is 6 inches long. How far does the tip of the minute hand move in 15 minutes? And then again, how far does it move in 25 minutes? So we're looking at how far does it move. So here's a picture of our clock. 15 minutes would be this distance in here. So we are looking for arc length here. So we're going to use the arc length formula to figure this out. We know S equals R theta. We've got to figure out what theta is to begin with. So we got to think about how much of a rotation is that? What angle are we looking at here? Well, in this case, we're looking at 90 degrees, right? Because we are moving 15 minutes out of the 60 minutes available, which is 1/4 of a revolution. And we know 1/4 of a revolution is 90 degrees because there's 360 degrees and we're looking at a quarter of that. So 360 divided by 4 would give me the 90. And if we want to turn that into radians, which we need for our formula, we're going to multiply it by pi over 180. And that's going to reduce to pi over 2. Now, they tell us that the minute hand is 6 inches long. That's our R value. So arc length is equal to R times theta. So we're going to get 3 pi inches for that. And if we wanted a decimal approximation, we could type that in the calculator. I'm going to do that off to the side. I got 9.42 inches for that one. Now, if we want to know how far does it move in 25 minutes, we're doing the same kind of thing. We've got to figure out first, what is our theta value here? So it's 25 minutes. We need to know what part of a revolution is that. So that's going to be out of 60 minutes. So what part of an hour is that? Well, that's 5/12 of an hour if we were to reduce that, which is really 5/12 of a revolution. One revolution is 360 degrees. So how many degrees is that? That's 150 degrees, but we need to, once again, turn this into radians. So we're going to end up with 5 pi over 6. So remember, S equals R theta. R is 6. That minute hand is still 6 inches long. So we're going to get 5 pi. And that's in inches. If we wanted a decimal, type it in your calculator. 5 pi is about 15.71. So in 25 minutes, that tip of that hand moves about 15.71 inches. Okay, let's look at one with a different flavor. Let's look at number 95. We have a water sprinkler that's spraying water over the distance of 30 feet while rotating through an angle of 135 degrees. We want to know what area of the lawn is receiving water. So we're looking for area here. Our area formula is A equals 1/2 R squared theta. So we know the radius is 30 feet, okay, because they told us the distance that this sprays. And we know the angle is 135, but we've got to turn that 135 degrees into radians, because remember, this formula uses radians. So set up our conversion. 135 divided by 180 reduces, so we're going to end up with 3 pi over 4 for that. So I've got 1/2 times 30 squared times 3 pi over 4. Let's simplify that. I got 675 pi over 2, and that's about 1,060.29 feet. Okay, let's look at 96. 96 has a different flavor to it. We want to cover an area of 100 square yards. It's going to be in the shape of a sector, so we're thinking about that slice of pie again. And the radius is going to be 15 yards. We want to know what theta is going to be. We have a formula that ties everything together. A equals 1/2 r squared theta. That's our area of a sector. We can substitute in what we know and figure out what theta would have to be. It's asking us what angle does the sprinkler need to rotate in this case. So we're looking for theta. So 15 squared is 225. Multiply both sides by 2 over 225. So theta is 200 divided by 225, which is 8 over 9. But remember, this guy's in radians, and perhaps they want this in degrees. We could turn that into degrees by multiplying by 180 over pi. And we're going to get a decimal approximation for that. So I'm going to use the approximates. And I got about 50.93 degrees there. So we need to rotate through almost 51 degrees in order to make that happen for that scenario. And let's look at another one. So we're going to be introduced to two new formulas here, angular speed and linear speed. I'm going to start by talking about angular speed. So when you're thinking about angular speed, I want you to think about how fast that central angle is rotating with respect to time. So we've got a wheel that's on an axle, kind of like on your car. How fast is that central angle changing? That's what angular speed is. When we talk about linear speed, it's really the measure of a distance traveled by an object. We've got formulas associated with these. So for linear speed, formula is pretty simple. Velocity equals s divided by t. S is your distance. So distance, think arc length there. Angular speed, you've got v equals r times omega. Omega is measured in radians per unit time. And omega is calculated by figuring out theta divided by t, where theta is in radians. So it's important to keep all of these different formulas straight and what the units have to be with respect to straight. So let's look at an example. Number 97. An object is traveling around a circle with a radius of 5 centimeters. If in 20 seconds the central angle with 1/3 radian is swept out, what is the angular speed of the object and what is the linear speed? So we know our radius is 5. We're looking at a time of 20 seconds. And the central angle, theta, is 1/3 of radians. Angular speed is equal to theta divided by t. So theta is 1/3, and that's in radians, out of 20 seconds. So we're going to get 1/60th radians per second. That's how fast that central angle is changing. Linear speed is going to be s over t. Okay, remember s is arc length, so that's r times theta divided by t. In this case, our radius is 5. Our theta is 1/3 divided by 60. So we have 5/3 divided by 60. And that's going to be, oh, I'm sorry, time is 20. I'm not sure where I got 60 from. Time is 20. So we have 5 divided by 60, which is 1/12. And that's going to be in centimeters. Okay, reason it's in centimeters is because that's what our radians was. That's what our radius was, centimeters per second. Okay, let's look at the Ferris wheel problem. You may want to take a minute, pause the video, and come back and check it. So let's talk about what we know. We know the radius is 30 feet. Now, we've got to figure out what it means for one revolution to be 70 seconds. So think about a Ferris wheel that has all these different seats on it. That means one revolution, let's say you're at the very top of the Ferris wheel. In 70 seconds, you'll go from the top all the way around back to the top again. So here's your seat. You're going to go all the way around back to the top again in 70 seconds. So we're traveling the entire circle, which is arc length, but it's also circumference in this case, right? So what is our circumference? Circumference equals pi times diameter, which is pi times 2 times the radius. Radius is 30. So in 70 seconds, we travel 60 pi feet. So let's figure out how fast that central angle is changing here. So that central angle would be this guy, right? How fast is this changing as this Ferris wheel goes around and around? So omega is equal to theta over t. Our theta is going all the way around the circle, okay? So we're going one complete revolution, which is going to be 2 pi. And that's every 70 seconds. So we're talking about pi over 35, and that's in radians per second. So my math lab's probably going to want that answer in terms of radians per second, but just to kind of put perspective on this, suppose we turn it into degrees, just to kind of give us a perspective here of how fast this thing's moving. If we were to reduce this, I got 5.14. So it's moving 5 degrees every second. So to figure out V, linear speed, is S over T. S is our arc length. We already said that was 60 pi. And T is 70. So we're traveling 6 pi over 7 feet per second.